Hello everyone, my name is Mikolaj Morzy. I'm from Poznań University of Technology. Thank you very much for being here to listen to this fairly short talk on demystifying AI tools. I'm representing Poznań University of Technology, so the technological leg of this project. And today I would like to shine a little bit of light and try to smooth out a lot of confusion that happens around AI. So let us begin. First of all, we need to clearly define what we mean when somebody says AI, because it has become such a common word, and it really can mean at least 10 different things. So in very, very broad terms, you will find ideas such as machine learning, supervised learning, unsupervised learning, generative AI, agentic AI, reinforcement learning. These are all types of teaching machines or creating algorithms that can perform or make decisions based on the data. Historically, we would divide the whole space into three main categories. We would say supervised learning, unsupervised learning, and reinforcement learning. The reinforcement learning basically is this idea of teaching the machine to achieve a given goal somehow autonomously by trying to optimize some kind of an objective function. Unsupervised learning and supervised learning are the types of learnings where you provide examples. Sometimes they are labeled. If they are labeled, then we're talking about supervised learning. If there is no supervision, if there's no teaching signal, then it's unsupervised learning. And again, historically, these two things, supervised and unsupervised learning, were called machine learning for some strange reason. Within supervised learning, two important different branches started to appear. One is called self-supervised learning, and another one is called semi-supervised learning, and I will get to these in a moment. And finally, the generative AI. This is a thing that has been with us for at least four last years, and it's a completely different thing. Right? So most of the hype when you hear about artificial intelligence will be, of course, on the side of companies that will sell you something which is akin to a slightly glorified Excel, but they will sell it as an artificial intelligence, but they will mean the machine learning, and most probably it will be predictive machine learning. Right? And this predictive AI, which is, by the way, the most dangerous from our perspective when we're thinking about the societal effects and the things that can go wrong. So let us go very briefly through these types. So reinforcement learning, this is basically when you see the computer play a computer game, right? The machine playing a computer game, all these publicity stunts with computers playing Atari games, running through the mazes and so on and so forth. But reinforcement learning was also a key part in developing modern algorithms that play Go, that play chess, but also the AlphaFold, the algorithm that creates the folding of protein molecules. This is also done by reinforcement learning. Reinforcement learning is a computationally super expensive. You need to make hundreds or millions of experiments, and it's not something that we would see in our everyday lives. An example given often is that you can imagine reinforcement learning to be used to teach, for instance, the autonomous vehicles, cars or drones to fly, but this is a little bit of a fairy tale because so many times the reinforcement learning fails. The agent that tries to learn fails the task. So when the computer learns to play the game, it dies millions of times before the machine is able to find the policy that guides it towards the reward. And the reward is postponed in time. So finishing the level in the computer game is a reward. The computer tries to different policies of how to get there, and it dies millions and millions of times. And after a million failures, it achieves success. So imagine crashing million Teslas before the Tesla learns how to drive, right? This is basically the idea. The generative AI, something completely new. is, of course, the language models, which we'll come to later because they are so prevalent. In terms of video and images, this is the ability and the algorithms such as, for instance, stable diffusion that are able to generate out of random noise images, and also that are able to to combine slightly videos and images. So you see the image of Emilia Eckhardt, and of course, she's never been caught on camera, and here you see her smile and move, right, a little bit. Or the lady in the lower right part, she doesn't exist, right? It's a completely generated image, but it exists. This part slowly starts to catch on. For instance, this is a mechanical part for motorcycles that has been developed last year by one of the motorcycle companies that asked generative AI to create a very, very specific part with very specific mechanical properties, right? It had to be very strong, it had to be flexible, it had to be, I don't know, it's a part of a motorcycle. I don't know which one, but basically you can use generative AI also to do manufacturing, and we will see more and more of that in coming days. Then we have unsupervised learning. The unsupervised learning is basically throw a bunch of data without any supervision, without any signal, without any information, and try to extract patterns from that. Whatever you can find will be good enough. Historically, the most popular task done via unsupervised learning was clustering, so trying to find groups of objects that are very, very similar to each other. And in the lower left part, you see clustering of a large MNIST data set. It is a set of small images of handwritten digits. So people were collecting hundreds of thousands of the ways people are drawing digits. These are very, very small pixelized images. And just by looking at these images, the algorithm is able to combine them together in some representation space. And the colors represent different digits. So you can see that the algorithm correctly puts the same digits together. So now when the handwritten envelope goes through the scanner just reads the digits, and the precision is like 99.9%. Recently, probably more important is the unsupervised learning of text representations. So let me briefly go here. This is the representation of a bunch of, let's see if I can do this using this internet here. Okay, when we're working with text, traditionally text has been understood as just sequences of characters. So without any, the computers were not able to extract any semantical meaning from the text, just characters and comparing character by character. But recently, by recently I mean since 2013, we are able to compute something which is called text embeddings, where texts are embedded in multidimensional space. Each text, each word is represented as a vector, and these vectors carry semantic meaning. So every dot in this image, here is a data set of 10,000 English words. Each word is represented as a point in multidimensional space. For the presentation reason, it's projected into three-dimensional space, but these vectors are much larger. These are 200-dimension words. And basically, what happens here is that if we search for a word, so let's search for some word, for instance, if we look for the word Poland, you'll see that the most similar words to Poland, oh, sorry, I have to probably choose it. So the closest words are the words such as Lithuania, Polish, Hungary, Germany, Russia in this space, which means that the space is able to represent semantic relationships between words. So let's go for something more like, yeah, let's see what chemical brings. So this is the word chemical, and very close to the word chemical, if we zoom in this representation, you will find the words such as compound reactions, biological, organic metals, hydrogen, substances. So you see, these are not random words, right? The words are put together close enough in this space when they share semantic meaning. It's not comparing character by character or anything like that. And this representation has been learned in an unsupervised way, so nobody ever told the machine, look, chemistry is really similar to reactions, or chemistry, the word chemistry and the word organic are somehow related to each other. The machine just extracted this knowledge looking at the vast amounts of textual data and looking at the collocations and co-occurrences of words. Right? This is expressed by the linguistic principle, which says that the meaning of the word is encoded, it's in its neighborhood. So you know, the correct quote is, you know the meaning of the word by the company it keeps. Right? So when you see two words occurring in the same contexts, that usually mean that they are semantically related to each other. But this is, again, this is very, very safe and not really interesting from our point of view. Then we get into the supervised learning. For supervised learning, you are given data and you are given a teaching signal. The signal comes in the form of a label. And this label categorizes elements into distinct sets of elements. The label can be categorical, so it can be, for instance, good, bad, mediocre, or healthy versus sick, or spam versus ham, whatever, or it can be numerical. So when given a numerical label, the problem becomes a regression, and with a regression, you are trying basically to fit the line that somehow summarizes a set of measurements, but with categorical data, you're trying to come up with the algorithm that, after teaching, given a new instance, will be able to correctly classify it into one of the classes. The famous example given by the father of contemporary statistics, Ronald Fisher, was the iris dataset. He collected 150 examples of irises, of flowers. These flowers represent 3 different species, Iris versicolor, setosa, and virginica. And what he did was he computed the length and width of sepals and petals. These are these little small flowers, parts of the iris flower. So each flower is described by just 4 numbers and the label. And the label is the correct classification into one of the iris subspecies. And then you can teach the machine to build a model that automatically, given the dimensions, it will be able to predict correctly the class, the species that it belongs to. There are over hundreds of algorithms of doing this type of task, of supervised learning. We usually refer to these tasks as classification, but you may also find the term predictive analytics or predictive AI used interchangeably. This is basically the same thing. Now, to give you an example, how can this be done? Again, let's take a look at a simple presentation. Let's train a simple model that will discover whether I'm sad or whether I'm happy. So in order to train such a model, first I would have to come up with a set of examples of me being happy. I would have to create examples of me being very sad, and hopefully after a little bit of training, the model will be able to tell whether I'm happy or sad. So we'll create a happy class. And now I have to teach it. So let's show the machine that I'm happy. So 100 samples of me being happy. Now let's show examples of me being sad. And let's train the model. This is the crucial part in the whole machine learning part. You have to collect the data. And this is where the peril is, because the data will never be as you think it is. It will be dirty, it will be noisy, it will encode all the cultural backgrounds that go with it. So we have the model. Yeah. So the model is now the model, as you can see, it runs between me being happy or sad. It doesn't matter, it doesn't know, so now it doesn't have a neutral stance, so that's why it by default goes to sad, because I'm Polish. But so you see the model knows that I'm happy, and I'm sad, and I'm happy, and I'm sad. Right? This is the whole idea. and self-supervised learning. Now, self-supervised learning combines the power of predictive AI, where you are able to predict something in the future without the need of supervision. And this is done by coming up with something called the pretext task that the model can learn itself. And by learning this thing, it learns something also very useful. So it's probably the easiest thing to show it on images. You take a bunch of images, you automatically turn them into grayscale. Right? This can be done automatically without any human intervention. And then you are showing these pairs of images. You show the black and white image and the corresponding color image. And you give it a couple of hundreds of thousands of examples. And hopefully, the model will learn how to colorize the images. But in order to learn how to colorize the images, the model will have to grasp some basic understanding of textures, of shapes, of the fact that the feathers are one color and the leaves are another color and the sky is another color and architecture is another color and so on and so on. So the task seems to be simply trying to colorize the image, but at the same time the model learns something about the shapes. Another thing is solving a jigsaw puzzle. So you take an image, you divide it into 3x3, 4x4, whatever, and then you just scramble the images. And the task of the model is to recreate the correct ordering of elements. So what is the knowledge that the model learns? It learns the topological relationships between elements in the image, right? It learns that the feet are usually below the head. Of course, it can be given an image of an animal lying on its back. Yeah, sure, and will probably cause an error in prediction. But in most cases, it will learn that the feet go down and the head goes up, right? The same can be done with predicting the relative position. Here, the task is, it's just computationally cheaper to do, and the effect is basically the same. So you take the image, you show the model just the center part of the image, and you show one of the 8 elements that go around. And the question is, the model has to learn the correct position. So it has to guess one of the 8 positions, right? So given the grizzly bear, we show the model is given just the centerpiece, so the nose. It is given a little bit, just a piece of the image. In this case, this is an ear. And the model has to learn that the ear goes here. So again, you see that the model learns the understanding of topological relationships between objects. It learns that the tires are on the down and the roof is on the top of the car. It learns where the ears are relative to feet and so on and so forth. A very simple self-learning is just guessing the correct rotation. So here you're the model has to learn has to guess one of the 4, which is again quite simple. The in-painting is more complex. So for in-painting, you're showing the images. You just mask a little bit of the image and asks the model to recreate the missing part, which is quite hard. And then there is also the semi-supervised learning. This is a situation where we have our data. There is a teaching signal, but it's far from complete. And the data labels that we can use for learning are completely unreliable. So the most obvious reason for that is that the labels are of low quality and very, very noisy. For instance, if people refer to crowdsourcing platforms to label things and solve simple tasks, the crowdfunding platforms such as Amazon Turk, and quite often if you need a really high quality labels, the labels that you need a lot of expertise to compute, then if you go to these low quality sites, the labels will also be of low quality. It could be that you have a lower granularity of labels. So for instance, in the ImageNet data set, you have over 1 million images and they are labeled with 1,000 concepts, describing the things you see in the world. So you might have a very general label such as a domestic animal or a dog even, and you want to train a model that recognizes breeds of dogs. So just knowing that something is a dog is not good enough. Right? You need a more specific label. It's good to be able to tell apart dogs from not dogs, and this is good enough, or this is very useful, but still not useful enough to get to a specific breed. You could have the situation where just a small part of the data set is labeled, which is also a problem, right? So given 1 million texts, you are able to, for instance, you're trying to build a model that prevents hate speech from being posted to an online site. And you were able to manually label 10,000 posts, right? And you have your annotation guidelines, and it's coherent, and you have annotators who are good at this task, and you come up with 10,000 labels for what constitutes a hate speech, but your data set consists of 1 million pieces, right? So then the question is how to propagate the labels from the ones you have to the unknown, assuming that there is a lot of similarity. And lastly, semi-supervised learning can be also conducted by programmatically generated labels. So you can write small, simple, there are libraries and tools that allow you to write small, fairly simple programs that analyze the data and produce the label. And of course, then you can apply and you can label the data sets of whatever size you want, but this comes at the cost because the labels are as good as your programs, right? So there is a little bit of bias encoded in that. So how intelligent and how safe these different types of AI are. So reinforcement learning is potentially interesting because there is potential for autonomy. At the heart of reinforcement learning is the search for the policy, not the direct solution of the problem, but rather trying to optimize the policy that guides the agent, right? The thing that is being taught to reach the solution. For the moment, it's rather simple, and we haven't seen any real-world successful examples of reinforcement learning, but this is definitely something to keep an eye on, because as we get more compute and as we get more sophistication and as we get better tools and better libraries, it could be that we will start seeing agents that are taught using reinforcement, different types of reinforcement learning in the future. Right now, probably you may associate the term reinforcement learning with the way that the output of large language models has been pruned. This is a very nasty story of terrible exploitation of people in Africa conducted by the Silicon Valley. But still, this is probably the one that comes to mind. But reinforcement learning can be done without any humans and should be done without any humans. And it could be interesting, but for the moment, it's not something that is on, on the crisp of creating the general artificial intelligence. Unsupervised learning is absolutely safe. It's very useful. It gives us nice representations. It can be used in different applications. It does not come with significant ethical concerns and risks, so it's absolutely fine. Supervised or predictive, that's the source of all problems, and I'll mention a couple of them in a moment. Generative AI, just totally hyped, with no good reason yet, but the yet here is the keyword, and agentic. This is probably the hottest term in artificial intelligence research over the last 6 months. Everybody is talking about the possibility of true agentic artificial intelligence, where we'll have semi-autonomous agents talking to each other and setting each other's policies. It is, again, very interesting. The large language models provide nice tooling for that, but it's just the very, very beginning. So first, simple demos of agents synchronizing calendars. Yeah, that's fine, but it is not, the Terminator level stuff, right? But again, it is potentially interesting. So why am I stressing the fact that predictive analytics or predictive AI or supervised learning is so dangerous, especially in the context of social sciences? Because it's really fine if you apply it to natural world phenomena, to physical processes. That's absolutely okay, because they are pretty much deterministic or close to deterministic, as close as one gets. But they all operate under a very, very simple assumption that the past resembles the future. So you're given a past data set and you extract the patterns and you assume that these patterns are valid in the future, which in case of social sciences is almost never true. So if you are ready to believe that the things that you have seen in the past are reflective of what is to be expected in the future, then yeah, fine, but pay attention and make sure that you understand all the risks. And also, there is so much overhype here that it's as nauseating. There is a German company that claims to be able to produce highly accurate assessments of workers in human resources based on 30-second videos on Zoom. And they were selling this for like, thousands of dollars. And of course, all the huge companies were saying, yeah, great, because we're not reading this shit anymore, the CVs that people sent us. So they try to connect us and we do the interviews, hiring interviews online. So if we just can push the interview through your software and the software tells us, yeah, this is a suitable candidate, this one is not, then perfect. Unfortunately, the researchers started playing with this software and it came out that just by keeping exactly the same interview, the same video, just making the background 5% darker caused the quality, the assessment of the quality of the candidate 25% lower. If you wanted to be evaluated much, much higher, you would have to put either glasses or a virtual background with books on. Just the books on, just the virtual bookshelf with books increased the assessment by 30%. Right? That's a pure snake oil, if you can see one. American systems are very interested in cutting the cost of patient care, and they are using predictive AI all over the place. For instance, there was a question of patients who were suffering from pneumonia in the hospitals, how long they should be kept in the hospital before being released, and the model consistently advised people to, if they had asthma, to be released earlier because asthmatic patients were supposedly in a much lower risk of catching pneumonia in the hospital, which makes absolutely no sense. And every medical professional on Earth knows that. But the software was so absolutely sure that if you are asthmatic, then it means that you're not in the risk of pneumonia. The problem was the data set that the model has been trained. It used the data set of patients from the hospital, but what the researchers and machine learning engineers did not understand was that the data set did not contain asthmatic patients because asthmatic patients were sent to the ICU right away when they entered the hospital because they were in such a high risk of catching pneumonia. And this is another example of just pure computer science hubris that I'll come back later. And predictive analytics or this supervised learning comes also, or it suffers from perverse incentives. The term perverse incentives, it's an economical term where you have your objective function defined in such a way that it creates an undesirable and unpredicted outcome. And of course, the best anecdotal example was during the British Raj in India, where the governor of the city of Delhi offered prizes for king cobra heads because there was too many cobras, so he offered incentives to kill the cobras. The result was that after 1 year, the population of cobras just quadrupled, right? Because people started breeding cobras. They were breeding cobras at home, killing them and bringing the heads to the governor. When the governor discovered it, it said, okay, no more payouts. So the people said, okay, so we don't need these 100 cobras at our house, and they just released it to on the streets, and the population of wild cobras just exploded for a couple of years. You might think that it is enough to do this example once, but the French did exactly the same thing in Vietnam when they were fighting the rat. The rat infestation, so they were paying for rat. They didn't want to have rat carcasses being brought to them, so they said, okay, just bring me the tail. If you cut the tail of a rat and put it back to the sewers, it will breed and you'll have more rats to cut the tails and get more money, right? So again, the only thing that happened was a huge number of rats without tails running through the sewers in Vietnam. And you see these examples everywhere. Just a couple of years ago, I think it was in the UK, they introduced the stipends that were supposed to lower, what was it? What was the big scandal? They pay the subsidies to make people not use the black coal for heating, but the subsidy was larger than the cost of the coal. So the companies started burning coal like crazy. In particular, they were heating empty buildings just to use as much coal as possible because they were getting more stipends from the coal than they were paying for the coal, right? Again, an example of stupid incentives. And I've mentioned the just pure hubris. This is a guy who won the Nobel Prize 2 years ago. This is the father of modern deep learning, or the neural networks, Jeff Hinton. In November 2016, he came up with this brilliant quote, saying that your kids should not go into radiology because, just in 5 years, it's completely obvious that machines will be much better. People should stop training radiologists now. It's obvious deep learning is going to be better than radiologists, and so on. So, care to guess what is the situation now in radiology today in 2024? Of course, there is a huge crisis and a lack of radiologists on the market. We are in a huge need of more radiologists. Right? Okay, so now let's finish with a short discussion about the large language models, because the generative AI is still the element that we haven't touched upon. And let me introduce you to a simple game. Now, I will start by saying something, and I would like you to shout out the first word that comes to your mind. Okay? So we begin. Better safe than sorry. This is pretty obvious. Are you American by any chance? Yeah. Since the recent administration, that has become a popular meme on TikTok. When someone says something extremely stupid, this is the first comment that comes up in the comment thread. The highest peak in Poland is? It is, very well. The second highest peak in Poland is? Okay, so what we've done here is we have trained a recently good large language model. The large language model, and the word model here is slightly confusing, it's just the machine that predicts the next word in a sequence of words. That's all there is, absolutely. All the DeepSeeks, all the chats, GPTs, everything. The only thing this machine does is it always predicts the next most probable word. How it works is that trained on an enormous amount of data, they just predict the next token, right? So given the simple fool me once, now the model goes through all the vocabulary, usually a couple of thousand of elements. The standard is 50,000 tokens, 50,000, well, let's say words. They are not exactly words, but let's say words. And then for each word, it computes the probability that this is the next word, and it could be set deterministically, so it will always pick the next most probable word in a greedy manner, but it could also randomly select using the probabilities, right? Proportional to the probability, trying to predict the next word. So fool me once, and Of course, you could say fool me once and fool me once because fool me once again. These are all absolutely valid constructs in English. They have non-zero probabilities, but since the proverb fool me once, shame on me, fool me, fool me once, shame on you, fool me twice, shame on me, this is so prevalent, then probably the word shame is the most probable here. And after selecting the word, the model goes again autoregressively and pushes the next fool me once, shame, and then again it goes through all the words and computes the probability of the words and picks the next most probable word for that. So it's really surprising that this simple thing produces such a powerful tool as ChatGPT. And nobody really understands it. It could be that we think too much of our intelligence. Maybe it is just the question of the language is so simple and our intelligence, which is encoded in our language, it is just the derivative of this simple process. Could be. Nobody knows. It is absolutely powerful. It's a very, very nice tool, but is it really intelligence, like artificial intelligence? And my take would be absolutely not. And let me just think as an engineer for a moment. So you have this large language model, right? So put there a GPT, ChatGPT, whatever. You have some inputs. There is a string of characters going into, and the model produces some output. It spews out something, right? It basically creates the next narrative, just continues the prompt that you were given. And then it has to go into something that controls the output. The output itself does nothing, like nothing, literally, is just a string of text. So there must be some module that makes a decision based on the output of the LLM. So let's call it a control module. And this module produces a feedback signal that can steer the next generation. So what is this control module? For the moment, at the simplest level, it's just prompting. So the prompt says, give me that, extract the names of rivers from this article. Evaluate if this article is positive or negative. There is absolutely no intelligence. It's just the next token prediction steered by a little bit of prompting. You have probably heard of LLMs that are being combined with external tools. The models that can use tools, can do website lookup, can use a calculator to do some calculation, can look up a database of knowledge, can go to Wikipedia or do some calculation on dates. So that would be the next level. You have some actions and you have some tools. Still, the control code is handwritten. There is someone who just programs it. That says, okay, if you see this kind of prompt, then take this piece, go to Wikipedia, search the article, find something, and go back, and then use it for another sequence of prompts. But still, there is no autonomy, there is no notion of state, so they are completely stateless. The model itself here, the one that is claimed to be artificial intelligence, again, does nothing by itself. It just accepts a little bit of text and produces a little bit of text, completely not knowing what is being sent as a feedback. Now, the next level would be agentic AI. And this is where the most hope is, that if we come up with tools to build the whole ecosystem for agents, the agents, which will be backed up by large language models to analyze and process text, images, videos, audio, signal, and so on, the agents will be more autonomous. Still, someone will have to, program the logic and incentives and objective functions for these agents, but there will be less direct human control over that. So you might start arguing, yeah, at this level, we may start talking about artificial intelligence. And the last level would be true knowledge. So the control module, whatever it will be, because we have no idea what it will be in a couple of years, should be able to either create or use the knowledge completely autonomously. But right now, we are basically at the lowest level, maybe at the first level, still far away from general artificial intelligence, and I absolutely don't believe any nonsense that there is some sentience in these models. It's just a simple machine. It just predicts the next word, nothing else. It's just what you did here. And by the way, the second highest peak in Poland is Mięguszowieckie Szczyty. All right, but they tell us that the next generation of models are reasoning models. These are the excerpts taken directly from OpenAI press releases. And yes, you tell me, press releases, they exaggerate a little bit, but still, they say, well, it's similar to human thinking, the model takes a long time before responding, the model is designed to spend more time thinking through. Are you shitting me? What does it even mean for the model to take more time? So what? Does it run on empty CPU cycles? It just goes into an empty loop and does nothing for a little bit and says, yeah, let's wait for 5 seconds and then continue with my CPU cycles. Like, it's pure nonsense. If you know how computers operate, that's just, so let's call it what it is. It's an absolute horseshit. It's nothing of what do you think. It is just the LLM, the same LLM that you've seen before, just more expensive for the end user. Why? Because the prompt is getting much longer, and you have to pay for every token that goes into the model. That's all there is. So let me show this to you. And we'll use here. So let's use our Chinese friend's latest invention. And let's ask the model a difficult question. Right? Let's come up with a question that probably has never been written in any textual source. So here is the question I will ask it. We can safely assume that no one has ever written such a text. Right? Who is the second most famous Polish poet of the Romantic era? Juliusz Słowacki, right. Where is he buried? Well, I came here, so I had to come up with an example involving Krakow, right? So yeah, he is buried here in Krakow. So we're asking about what is the official dog-to-human ratio in Krakow, but in a very cryptic way. And let's see what the model tells us. Okay? So, great reasoning, right? How did the model came up with this idea? Well, a couple of years ago, researchers have observed that these large language models are much better when, instead of trying to address the question directly, they break the question into small parts, into simple steps that can be conducted one after another. So basically, all this reasoning means the model has been trained, explicitly trained, to break every single question into subsequent steps, and it goes through these steps. So the model starts with the first step. Identify the second most famous Polish Romantic poet. How many times you see the text about the two most important Polish Romantic poets are Mickiewicz and Słowacki. The second most important poet is Słowacki, right? The Słowacki, always the second, always the silver medal, right? Never the gold. So yeah, the model learns that it is Juliusz Słowacki. Determine where, and now we are not talking about the second most famous Polish poet. No, now we're talking about a very concrete tokenization. Juliusz Słowacki. Where is Słowacki buried? Again, thousands of textual sources that tell us where Słowacki was buried. He was buried in Wawel, Krakow, right? Wawel Cathedral in Krakow. So the conclusion, the city in question is Krakow. So find Krakow's human population. Now you need just two things. You need the dog population and you need a human population. For human population, you go to Wikipedia or Polish Central Statistical Office and you get the information that 800,000 people live here. Now we have to estimate the Krakow's dog's population. Now I have seen this model also go into some city of Krakow sources to get the exact number. So here is just the estimates that there is one dog per 6 or 10 people, but I've seen also this model go into much more detailed estimates, and that's it. And then you calculate the ratio, which is simple. Now, the company tells you, oh, it's such a deep thinker, this our latest model. But the truth is, it's the same model. It's exactly the same model that you use. But the first model costs you like 5 cents per 1 million tokens. And here, you will pay more because they will expand your prompt. You enter a simple prompt, and behind the scenes, the company expands your prompt into something like that, this huge, long prompt being the chain of thought, one step after another, after another, after another. They run this prompt through the model, and they get to the result. But you pay for this prompt. You have entered 100 characters. They change it to 10,000 characters, and you're paying for 10,000 characters. And you can see this directly if you go to the OpenAI license, and you see that they introduce the invisible token costs. And it's just, a fiat. They tell you to pay $20, and you pay $20. Why? Well, because it's hidden costs, right? It's like, American health insurance. You never know. So the model seems to be such wonderful and great thing. So let's finally put it to the test. So there you have it. This is a true artificial intelligence. If you're searching for one, yeah, this is one. Ask the DeepSeek about Tiananmen massacre, and you get interesting results. Yeah, okay. So is it okay to panic right now? It's probably not, and I'll leave you with one food for thought, namely, how do you think it goes? Is it the crows croaking that brings the sun up, or is it the sun going up, rising up, making the cock to crow? It's a difficult question, if you ask me, if you have only observational data. Because in the observational data, you will have several days, and some days the sun was rising and the cock was not crowing. There were days where the sun was rising and the cock was crowing. Sometimes the cock was crowing slightly a little bit before the sun rose. Sometimes it croaked a little bit after the sun rose. Sometimes the cock was crowing and the sun was not going up at all. Right? Because the cock was crowing in the middle of the night, or for instance, it was completely dark, or it was completely cloudy. So it's really hard to say. There is no way to tell which way the true causality arrow points. Right? It's just association. It's just correlation. And you've heard it times and times again that correlation does not mean causation at all. And this is many believe that this is the most fundamental problem in all artificial intelligence, that if we can make models really grasp the idea of causality, then this is the way to bring true the real real artificial intelligence. These correlations, sometimes they are really strange. Right? For instance, there is a true correlation between the number of storks and the number of babies being born. It is firm, and if you go to the data, it's very, very strong. Right? So maybe this is the reason why people believe that the storks are bringing the babies, although I was told that I was found in the field of cabbage. Maybe it's the Poznań, the Western Poland kind of stuff, but yeah. But there is this correlation. There was an ongoing discussion between the father of modern statistics, the Ronald Fisher, and the UK Surgeon General about what causes cancer. So you have 3 different variables. So it might be your genes, it might be the fact that you are smoking, and there is a variable that says whether you have lung cancer or not. And the question is where the causality goes, right? Because only these 2 things are observable. you don't observe genes directly. So the question is, and it was a fierce battle between Fisher and the Surgeon General. It was in the 1950s. Fisher was absolutely convinced that the true causal graph is on the left-hand side here, that there is a confounder in the terms of genes, that genes causally make you more prevalent to smoking, and the genes can cause cancer, and that there is no causal relationship between smoking and lung cancer. While the Surgeon General was absolutely convinced that there is only one causal link here, and it's a direct link between smoking and lung cancer, with genes having nothing to do with it. Now, maybe it didn't help that Fisher was a chain smoker and he smoked, like all the time during the day. So maybe there is a little bit of trying to counter the reality. But yeah, today we have there is no more discussion. We know that Surgeon General was right, but you can see these discussions about the causal structure of the world going on and on in the data. And this is the final slide, which shows you that right now we are here at the level of observations. We have observable data, and all the models and everything that we do, the predictive AI, the generative AI, they all work only on observations. They have no ability to do any intervention. For intervention, of course, it's just like a randomized controlled trial, right? You set the variable, you freeze it, you change something in the world, and you see what happens. And sometimes you can do this, sometimes you can't, right? Sometimes it's infeasible, sometimes it's unethical. You cannot force people to smoke or not smoke and see whether they get cancer or not, right? Obviously. But in many cases, at least in computer science, in simulations, for instance, you could come up with interventions and try to bring this, go one level up on the ladder of causality. And even higher on the ladder of causality are counterfactuals. So let's put it into a simple example. I didn't take a pill 2 hours ago and my head is hurting. This is the observational data. This is the only reality we have. Right? Then we could do the intervention. I could have taken the pill or not taken the pill and then see whether my head hurts. Now, counterfactual would be one level up. That would be saying, had I taken the pill 2 hours ago, my head wouldn't be hurting right now. But this reality, this universe in which I have taken the pill 2 hours ago does not exist. Still, we as humans create these counterfactual realities all the time. This is something completely missing from artificial intelligence. These models they don't even come close to this ability. And many people claim that in order to get the real ability to reason and for the true artificial intelligence to be born, we have to come up with the ways to make the models climb this ladder of causality, because right now they are all operating only on the observational data. That's basically it. Okay, and I believe that I've exceeded my time by roughly 3 minutes. So. No, you're absolutely on spot. I would say that this is exactly why I'm thinking the reinforcement learning thing is the most promising area worth looking at, because this is exactly what reinforcement learning does. It runs many experiments and tries different things, maybe not in the way we are accustomed to in terms of like pure A/B testing. It's more like policy testing, whether this general policy works better than not, but still it's in the spirit of exactly this one, right? So yeah, the next one, the predictive AI, the models used for scoring the CVs, patient scoring, credit risk scoring, and so on. These are on purely observational data. There was no experiment but even those models, they begin to experiment a little bit due to the regulations, because after the regulatory bodies introduced the need to explain algorithmic decisions, these models have to go into a little bit of intervention saying, you were denied the credit because you are described by these 10 variables, your age, gender, your income, your marital status, and so on and so forth. But should your marital status be slightly different, our decision would be another one. So they can show you, for instance, the variable that most influenced the prediction. Right? So it was your age. We deny you the mortgage because you are too old and we don't think you can pay it out. So they move a little bit on this ladder, but there's, in my opinion, there is a long, long way to go. Yeah, this is probably the biggest concern of big companies right now, that we are very quickly approaching the limit of available data, the real data, and that becomes the biggest cost in training and gathering, because these are already in terms of petabytes of data that we are crawling. And yes, true, the explosion of generated content is, this is probably the last 2 years. I don't think I have seen any reasonable solutions to this problem. It's learning on your, like the model regurgitates what it has already seen. Probably for the time being, they will do what they always do. So they will hire people in Africa for $1 per hour just to sieve through the data and do this reinforcement learning with human feedback, which basically means take people, pay them nothing, and make them look at terrible images and terrible texts just to label them as not acceptable, for instance, right? This is the story of this American company that used people in Nairobi. I believe they were paying them like $1, $1.50 per hour, and the people were like reading through the most obnoxious, racist stuff just to see that it's racist, right? And these like people reading this for $1. So probably this is the easiest thing to do, right? Just, again, hire more people and let them filter through this shit and tell them, try to tell what's real from what's been learned from generated AI. But I have no idea. And this is becoming a true problem. Amazon has no idea how to cope with the flood of chat-generated ebooks in self-publishing that are flooding the service. Right? You can buy, for $1, you can buy a mushroom picking encyclopedia, which will kill you instantly, because like they just generated it, and there are hundreds of examples of highly poisonous mushrooms that are described as absolutely delicious. Just put them into, eat them and enjoy them. And you'll see this in every, like in science, right? We see already journals and conferences struggling with AI-generated not only articles but reviews as well, right? So the basis, the foundation of the whole scientific publishing is crumbling right now under our feet, right? So, yeah, but I have no idea how to answer it. It's just